Most of the experiments that I've discussed so far have been done by colliding particles. And I said earlier on that very little of what CERN does is really nuclear physics anymore. But one of the things that CERN does do is experiments colliding nuclei at extremely high energies. And as you can see in the top left picture, when you collide nuclei at very high energies, you get a big mess. Well, what we believe is going on is that protons and neutrons, the constituents of nuclei, are actually being melted, and that what is happening is that you're producing a plasma made up out of the quark and gluon constituents which are inside the protons and neutrons. And experiments at CERN in the 1990s, culminating in the year 2000, produced a number of pieces of evidence that suggested that some sort of quark-gluon matter was being produced in these collisions. Again, you may say, I'm happy with nuclei. Why do I care that there may be a quark-gluon plasma? Again, the answer comes back to the early universe. The universe, in its first microseconds, would have been so hot and so dense that we believe that the state of the universe at that time was precisely this quark-gluon plasma. So in some sense, these experiments at CERN, and now they're being continued in the United States, can be regarded as little bangs recreating the conditions which obtained in the Big Bang. I've said there's very little antimatter in the universe. Probably the largest amounts of antimatter in the universe are those in particle accelerator laboratories, and in particular at CERN. And one of the experiments at CERN that produced a big noise in the 1990s and in the last couple of years has been the production of anti-atoms. I think actually we were a little bit surprised by this. When this discovery was announced, I don't think CERN anticipated the media reaction. When people hear about antimatter, they think of Star Trek. Unfortunately, with a handful of antimatter particles, you wouldn't be able to get the Starship Enterprise to move very far. When we talk of industrial production, we're only still talking about production of less than 1 million anti-hydrogen atoms. So, we don't see the immediate use of this, the same way that Rutherford didn't understand what his work was going to be useful for. However, we plan to do basic research on this to understand, again, the difference between matter and antimatter. Okay, so I've given you a sort of telescopic survey of some of CERN's basic scientific results, advertising some of the implications for cosmology and astrophysics. Now what I'd like to do is to move on to discuss the impact on society, and I've chosen 2 or 3 separate subjects, the first of which is computing. Clearly, to do experiments in particle physics, you need state-of-the-art computing facilities. And the first stage in this was a supercomputer. And this is a rather lovely picture of the first supercomputer being delivered at Geneva Airport, coming out of the mouth of this airplane. However, supercomputers are no longer fashionable. Instead, the trend is towards shared computing resources. And this development towards shared computing resources is something where I think CERN has been leading the way, just driven by the requirement of doing the physics. The most famous example is, of course, the invention of the World Wide Web by Tim Berners-Lee, shown in this picture here. Another development, which has already been alluded to, was the development of farms of distributed PCs during parallel computing, which was also pioneered at CERN in the 1990s. And the next development is the grid. This is the idea of connecting computers, even simple PCs, around the world to really share computer resources, not just to download data from a website, but to really use the CPUs, the memories, and all the other computing resources around the world. This idea of the computing grid is not something which originated at CERN, but within Europe, the European Union has asked CERN to lead the development of the grid. So another couple of pictures from our archives. On the left, you see amazed computer scientists in the United States making the first download of a web page from CERN. And on the right, you see the computer from which they were downloading, which is the first World Wide Web server. This was back in 1990. CERN, of course, having originated the World Wide Web, I mean, this was something which was much bigger than CERN could possibly manage. And in fact, very soon after the invention of the World Wide Web, the EU funded web research at CERN. This was during the mandate of Chris Smith as Director General. So as I mentioned, now we're moving on from the web, which provides you access to documents, to the grid, which provides you with flexible, high-performance access to all possible interesting resources. With the grid, you will be able to say, I want to do an analysis, maybe of some complicated environmental problem. From your workstation, you will locate the software, which may be, I know, somewhere in China. You will locate CPUs, which might be distributed through Japan, India, and the United States. The grid will do the calculation for you on these many, perhaps thousands of computers around the world, and then it will return the result to your workstation without you having to do all the donkey work of organizing the calculation. So the driver for this in Europe is particle physics, and it is the tremendous data which are going to be produced by the LHC experiments when they come into operation. And this sketch here illustrates how the LHC computing grid is being organized. There will be some central high-level computer center at CERN, and then this will be surrounded in a sort of virtual computing organizations of various layers, or tiers as they're called, of computing centers extending down to individual workstations on the desktop. This is something that has to be there in 2007 when the LHC experiments start taking data. And once it is there, then the techniques that have been developed to deploy the grid will then be applicable to many other sciences. This shows you the status of this LHC computing grid as it was last month. 82 sites around the world, over 7,000 computers connected, and all able to work together, for example, for the simulation of possible experiments at the LHC. I just might mention a few of the ways in which this grid development work can be used in other areas of science: medical and healthcare, bioinformatics, nanotechnology, engineering, the environment. And in fact, the EU has asked CERN to work with scientists from these other areas to deploy the grid for e-science throughout Europe. We mention another example of the impact of CERN on society in medicine. There are many applications of physics nowadays to medicine. And let me just mention a few where CERN has been or is making contributions. One is the use of accelerators for therapy. One is the development of detectors for diagnostics. In fact, CERN was one of the pioneers in positron emission tomography, or PET, which is now widely used in hospitals. And CERN is actively developing detectors which could be used with next generation PET and other diagnostics. Isotope production. Many hospitals around the world have small accelerators for producing isotopes. The grid can be applied to medicine, and there is a project funded by the EU based at CERN called MammoGrid, which is working on the integration of medical databases and their analysis. So let me just illustrate these examples in a little bit more detail. People are familiar with radiotherapy. At CERN, we've been involved in pioneering hadron therapy. Why is hadron therapy interesting? Hadron therapy is interesting because, as you can see in this picture, the energy deposited by a hadron, a proton, in living tissue is very concentrated at one place. This enables you to eliminate tumor cells, in principle, without damaging normal cells. If you irradiate in normal radiotherapy, you tend to get a large physical dose near the surface. The biological effect is not what you want. The effect is not localized in the tissue which you're trying to attack. However, with hadrons, with protons, the dose is highest at the peak energy deposition. The DNA damage which is done is not repaired, the high biological effect, and the effect is localized just where you want it. CERN, in fact, led a study which came to a design for a possible proton and heavy ion medical machine called PIMS, which would be able to accelerate both protons and carbon ions. This was done in collaboration starting in 1996 with groups in Austria and Italy. And in fact, there are now medical accelerators under construction, in particular in Italy, which are based on this PIMS design. The study was hosted and supported by CERN, and many CERN staff members contributed to it. And other such facilities are now being planned in Europe, such as one in the Czech Republic and also in Germany. I mentioned positron emission tomography. I think many people know about this technique where you use a radioactive source which produces positrons. The positrons annihilate, for example, inside your brain. They produce photons. These photons then can be detected, and this enables you to do diagnostics inside living tissue. This is something which was initiated in the United States, but much of the early work was done at CERN, also in collaboration with Geneva Hospital. And one of the things that CERN is now active in is trying to find better detectors to work with PET and other diagnostic tools. One line of research is called MEDIPICS. This is one where you use solid-state detectors of the type which were developed for particle physics experiments, specifically the LHC experiments. Another example is using crystals to detect photons. This is something which was developed extensively at CERN in the 1980s for the previous generation of LEP experiments. During the 1990s, it was developed for use in the CMS experiment at the LHC, and not the same crystals, but the same technology can also be used for medical applications. And as I already mentioned, developments in computer technology, such as the grid, can also be used for medical applications. Hospitals now are generating enormous amounts of data from many different types of imaging and diagnostic tools. These things have to be combined. Often you want somebody a long way away to look at these images and help you with the diagnostics and recommending treatment. You want to conduct studies of many thousands, perhaps many millions of cases to compare what happens so that you can give a prognosis. All these require intensive computer tools. And the EU has set up a project based at CERN called MammoGrid to explore the application of grid technologies for this purpose. CERN is an educator. This picture here, which I rather like, shows young people, and also maybe some slightly older people, running around CERN in our annual relay race. Why are there so many young people at CERN? Of course, they're students of particle physics. CERN operates many different courses, many different educational programs for these people at the undergraduate level, graduate student level, and after getting PhDs. I said there's a lot of them. This picture actually shows you how many there are. This is a snapshot showing that the mode of the age distribution for scientists using CERN is under 30. We have literally thousands of students coming through CERN, and over on the right-hand side of this picture, you see that there are also a few professors, but obviously not all the students become professors, right? So what do? Well, most of them actually go into industry. Some of them go into universities, some of them go into research centers. The ones that go into industry go into a variety of different things. Many go into computing, electronics, chemistry. Perhaps one of the most surprising slices of this pie is the fraction that go into finance. In fact, the Deutsche Bank has run advertisements in the CERN magazine inviting young people at CERN to apply for jobs in banking. Impact on international relations. CERN has been in the business of accelerating particles across frontiers for many years. Our accelerators go across the Swiss-French border, and this is actually a picture of the SPS accelerator as it came through the border. I'm not sure that the girl in the middle was actually part of the construction crew. I've already mentioned that CERN was the first European international organization. Predated the EU, and it became a model for many other international scientific organizations, such as European Southern Observatory. During the Cold War, it was an important meeting ground between East and West, and this has already been mentioned by Professor Kulikovsky in his introduction. It was a place where physicists from the Soviet Union and the US could meet. Perhaps not a coincidence that the Pugwash conferences for many years were held in Geneva. One of our directors general was Professor Weisskopf, was very active in the Pugwash movement. CERN sent experimental group to work in Russia starting in 1967. As has also been mentioned, CERN opened up to Central Europe after the fall of the Berlin Wall. Many Central European countries became members of CERN starting in 1991, Bulgaria more recently in 1999. As I've mentioned, I think the LHC was truly the first global scientific project with participation from dozens of countries around the world. This participation bridges many political divides. We have physicists from the US working with Iranians. We have physicists from Israel working with Moroccans. We have physicists from China working with physicists from Taiwan. We have physicists from India working with people from Pakistan, and I could go on. For example, this summer we had some students from the United Arab Emirates, and 2 of them were assigned to work with an Israeli supervisor. No problem, but where else would it happen? I will stop discussing what I might regard as the spin-offs from particle physics, and I want to come back for the last few minutes to, again, the core business of CERN, which is particle physics. And I want to finish off by just mentioning some of the open problems in particle physics that all these people from Israel, Iran, China, Japan, and Poland are wanting to work on. What is the origin of particle masses? Some particles, like Einstein's photon, have 0 mass. Some particles, such as Carlo Rubio's W and Z, are very heavy. Why are some particles massless and some particles heavy? We believe that there is another particle out there which provides the masses for all the known particles, something called the Higgs boson, and this is one of the principal objectives of the next generation of experiments at CERN with the LHC. There are good reasons to think that this particle should exist and should weigh less than about 1,000 times the proton, and this sets the energy scale for the LHC accelerator. Why are there so many different types of matter particles? I said earlier on, CERN established there are 3 types of neutrinos. Why 3? Why not 2? Why not 5? We know there are 3, but we don't know why. Maybe this is linked to the subtle differences between matter and antimatter that I mentioned on 1 or 2 occasions. We've made some advances with the unification of the fundamental forces. The weak and the electromagnetic force have been unified, but still waiting is the unification with the strong nuclear force, which we believe may only be possible at some extremely high energy. And eventually, we hope, of course, to find a quantum theory of gravity, put that together with the other interactions. But for the moment, our ideas about how to do this remain speculation. So this is the main agenda, I would say, of particle physicists at the moment, and in particular, the agenda of experiments at CERN. I'll say a little bit more about the problem of mass. You may say, well, don't we understand mass? I mean, Newton, after all, told us that weight was proportional to mass, W equals mg. Kids learn that in high school. Unfortunately, what the kids do not learn in high school, because Newton didn't know, was where the mass comes from. For him, the mass was just a parameter. Einstein, he told us that energy is related to mass, E equals mc squared. But he also didn't explain where the mass came from. What for me is a real key question is what other particles may exist that the LHC can also find. And I think one of the most interesting topics is dark matter. This will be discussed in more detail by subsequent speakers. There are good reasons to think that the universe is full of dark matter, which is much more, weighs a lot more than regular matter. This is very likely to consist of particles which weigh less than 1,000 times the proton mass, and one of the options is that they are made out of what we call supersymmetric particles, which we can look for with the LHC. So this is in fact, personally, this is the thing which I'm most interested in learning about at the LHC. I hope I've convinced you that the next steps in particle physics, the discovery of the Higgs boson, the discovery of supersymmetry, might be interesting, and that they're going to need a higher energy accelerator, and this will be the LHC, and that will be the subject of the next talk. Thank you.